Good day, everybody. Thanks a lot for inviting to give a speech here. I'm really happy to be here and all the time also to follow the development of photonic everything. And I'm really happy about the new space chair project. So really looking forward for next year's how it will develop. Here I give a short presentation. So I was asking Arnold if I should talk more about Ventspils or some other things, and he said I better talk about other things. Yes, so probably Dmitry will tell a bit about Ventspils then. But I still have one slide with Irbene. So I will give a bit talk about plasma energization in solar wind and Earth magnetosphere. This is for me close topic, so I'll give a few slides on history and a few slides on the last recent things with the space missions that is happening there. So in the background, you see nice aurora, and of course, I will come back why aurora has to do with a solar wind and Earth magnetosphere. Let's see how I can forward. These are pictures, by the way, taken in Irbene. Yes, so this is a site not far from Ventspils University, Ventspils, where we have the radio telescopes. And last May, so 1 year ago in May, taken by a normal photo camera. It's not taken by me, it's some school children who have been there and taken pictures. So because we are still in April, so there are very good chances still to take nice pictures of aurora. But let's go back. So a few weeks ago, 29th of March, we had a solar eclipse. Yes, so it was a partial eclipse. Really nice event to do advertising for space, for research, for students. So we had also an event in Ventspils. So it was, I think, 50 or more persons attending it. It was a partial eclipse. It was not a total eclipse, but still you could observe nicely the eclipse. This is a picture taken by telescope. Yeah, people looking on the sun. Very nice event. This is a picture of a full eclipse. This was 2019. It's not picture taken by mine. This is how it can look like a full eclipse. If we zoom in a bit, this is how it looks like a full eclipse. If you have a moon in front of the sun, then nicely you can see the corona of the sun. And such pictures one could take well before the space age. And it means light which you observe here, this is a Thomson scattering from electrons in the solar corona. So just by seeing how much light is scattered, you can tell how many electrons are there. So it means already well before space age, you could make a density model, how density of electrons is evolving from the sun, yes? Based on that, so here is a paper, 1937, one has some empirical model how density extends from the sun, just from eclipse data. Based on that, if you assume that things are in equilibrium in corona, you are concluding 1941, well before space age, that corona is well above 1 million degrees hot. So to keep it like that, the density structure, it should be more than 1 million degrees hot. So this is a paper by Hans Alven at that time, yes, so it's 1 million degrees. Yeah, by the way, these old papers, they're really nice, the way how they're written. I will show another paper by him. The funny thing is that the sun itself is 5,800, maybe where you have a sunspot, you have 4,000 degrees. So corona, 1 million degrees, but the sun itself is just 6,000 degrees. So the question is why? So this is a video. Yes, you can see how one sunspot and one can see how corona granulation is working. So activity on the sun, yes, but so here in the center we have something like 4,000, here is like 6,000 degrees, but as soon as you go above, it's 1 million degrees. If you look on the temperature, so very shortly, so this is the sun. If we look the red, the atmosphere, so this is the red here, yes, the height above the photosphere, 100 kilometers, 1,000, 10,000, 100,000 kilometers, and here's the electron temperature, yes. So when you are close to the surface of the sun, yes, so temperature here in the Kelvin, so this is 10,000 degrees. So here are these 6,000 degrees, yes, close to the sun, 6,000 degrees. And as soon as you have like 20,000 kilometers above the surface of the sun, temperature goes up to 1 million degrees, and it continues to heat up. You see temperature is going up. Then it reaches a peak, and then of course, when it comes to the Earth, it decreases. But here you see, like when you're at 100,000 kilometer altitude, 1 million degrees. Yes, by the way, it means if you look here, of course, what it means when you have these hot temperatures, people in the audience here understand them directly that it means here you have a plasma. So basically you have a plasma state, everything, you have a charged gas. The surface of the sun, there the density of neutrals dominate. So basically the surface of the sun, that's the place where you have a neutral matter in a neutral state. But as soon as you go deeper in the sun, temperature increases, and then also everything is in a plasma state. So basically inside of the sun, everything is in a plasma, and as soon as you go more than 20,000 kilometers above the surface of the sun, you have corona, everything is in a plasma state. And if you look on the universe, most of the baryonic matter that we know, which is not dark matter, is in plasma state. Here is an example, galactic cluster, yes. So optical pictures, the blue dots, that's where you have galaxies. And in a red is X-ray, which means this is a hot plasma, 100 million degrees, yes. And it is filling all this volume between the galaxies. And that's where baryonic mass is sitting. So if we want to understand universe, we really need to understand the plasma, yes. What's this hot, in this case, 100 million degree plasma is doing. Okay, so, and what is the source of it? What is like the series? How do we heat up? And one of the basic things is how one believes is that it is due to the Alfvén waves. So this was Hannes Alfvén. This is how Alfvén wave can look like. Unfortunately, this sharing doesn't work, but you can see that this is like a curtain waving, yes? The blue dots is electrons, red dots is ions, and black lines are magnetic field lines. So Alfvén wave, you can think in the plasma as propagating, it's some kind of curtain. So where electrons, ions, and magnetic field move together. That's basically Alfvén wave. By the way, this is a paper showing the existence of Alfvén waves. So the paper was written 42, I think, yes, here, 42. This is the whole paper, half a page of the, and it has everything, introduction, applications, theory. So here is even by elementary calculations. Yes, one is deriving it after the quantum age. For this, he got a Nobel Prize, basically for this discovery of Alfvén waves. And Alfvén waves, one thinks, is also the source, which is like causing this heating of the solar corona. Let me see, think. So 1 million degrees, how it is heated. It was already suggested by Alfvén, 47. It should be magnetohydrodynamic heating. If we move in time, like 60, 70 years later, if you look what our theories now, how we understand why it's heating, we are still there. Well, of course, we have much more data, we have much better simulations, we have much better observations. I will show some of them there, but we are still thinking that the reason why this heating is occurring in chromosphere and corona, it is due to, and the only difference before it was magnetohydrodynamic, now it's called Alfvén wave, because his contribution was so important, so those waves now one calls for Alfvén waves. So this is a basic idea also how one still thinks, how you are heating the plasma, it is due to the waves. So sun is generating Alfvén waves, and these waves are damped, and that's the way how you heat the corona. And as you saw, the surface of the sun is boiling all the time, plasma is moving, convection, everything, this is generating these kind of waves, and then they're damped and heating the corona. When you have this hot corona, and here you can see that like if you have 1 million degrees, then Parker 58 showed that if you have hot thing, it should expand. And if it is expanding, it should then obtain velocity, which is like 400 kilometers per second. So basically we have a solar wind. So this hot coronas that we have around the sun, it should expand speed around 400 kilometers per second. For this, he got a Crawford Prize. So he died in 2022. Parker, and it's important to remember the name. because I will return to this. So now about the solar wind, 400 kilometers per second. Again, this one could discover already before the Parker. And the way how you could discover that there should be a solar wind, this is just watching the comet. So this is from already like in the paper 50, photo is not from 51, but paper already by Biermann 51 suggests there should be solar wind 400 kilometers per second. And this is if you take a picture of comet, there are two tails. One is dust tail and another is iron tail. So basically dust tail is when comet is moving around the sun. So what you are left in orbit, the dust which basically goes in the same orbit as the comet. But then you have an iron tail, which is pointing away from the sun. And it is pointing away from the sun because the ions which are generated at the comet, they're picked up by a solar wind and basically propagate with the solar wind speed. So looking at the angle, how this iron tail is tilted with respect to radial direction, one could already tell how fast this solar wind speed should be. Well, before the space age, just looking on the comets, yes? So one knew there should be solar wind. When one launched the first spacecraft, 1962, yes, this is the measurements. So one, of course, observed there is a solar wind, 400 kilometers per second. It's varying, it's blowing away. But then we come to Parker solar probe. So here is the name Parker, yes, what I was showing you before the paper. So what one wants to understand, so one has this theory, but of course one needs the data and one wants to understand how exactly you get heated, how exactly the solar wind is generated. So one wants to come closer and closer to the sun. And this is a mission which is currently the closest mission to the sun. So it comes as close as 10 solar radii. It's a NASA mission. So this is how it looks like. There is a thermal shield, yes, and there is some antennas measuring electric fields, magnetic fields, plasma particles, and there is a camera which is watching sideways because you cannot watch towards the sun. Everything is melting. There is just a thermal shield there, yes. Okay, it was launched 2018. And this is the orbit, how it orbits. So what it does, you do not have enough propellant to directly go as close as possible to the sun. What you do, you use flybys of Venus to decrease your perihelion so that you're coming closer and closer and closer to the sun. So after every flyby of Venus, so here is an orbit, this is perihelion, this is apohelion, here is Earth when it's launched. And then when you have a flyby, the perihelion comes closer. You have a flyby closer, 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 and we are here somewhere. So this is the last flyby was last year of the Venus, and now we are at the closest distances possible to the sun. This is how it looks like if you have a PR person, yes, so nice spacecraft flying past the sun, watching the source of the solar wind and how it's heating. Now, if you look in reality, so this was from the movie, yes, but in reality, if this is a sun, spacecraft is approximately at such a distance, yes. So it's like 9 solar radii from the sun, yes, which is the closest approach. But it's really close. So this is really important because we are really coming to the source of the solar wind as never before. And by the way, now this is the fastest man-made, or let's put like the fastest space object that civilization has. So the speed when you are at perihelion is 192 kilometers per second. Quite fast. If you think about technical challenges, if you're at perihelion, then for example, the solar power is 475 times higher than at the Earth. So you have something like 650 kilowatts per square meter, which is sun pushing. There is another mission also, which is going for the sources of the solar wind. And this is Solar Orbiter. This is done by ESA, launched 2020 recently. That goes only to 60 solar radii. But this here you can see it's a thermal shield. There is a spacecraft. Yes, this is from the backside. The good thing is that because it doesn't go so close, it still goes close, but not so close. Now one can have in this thermal shield some holes. And basically, you can have some holes to have a telescopes there. So you have different visible, ultraviolet, X-ray telescopes observing the sun at the same time as you have also payload to measure the plasma, electric, magnetic fields, and plasma particles. Yes. So now it's like a golden age for solar wind studies in that sense. So you have this solar orbiter, you have plasma solar probe, which is so close. Yes. So last Christmas was this first closest approach to the sun. So really we are like entering the nice golden age for the solar wind source studies. This is some example of pictures taken from the sun, yes, from the solar orbiter, how very high details of extreme ultraviolet. This is a bit more instrumentations. I myself was involved in one electronics card, yes, designing. I'm not electronics engineer, I'm a scientist, but I was developing electronics card, which is steering electric field measurements by these antennas. So DC electric field measurements in a plasma. So just to show some data from these missions. So this is example of older missions. And from older missions, what we know is that if this is the sun and then you have different planets, so you have had missions at different distances from the sun. And this is the closest to the sun, Helios, 0.3 AU. This is at Earth, 1 AU, and this is Ulysses at 2.4 AU. You can see this is velocity of the solar wind. Farther away you get, smoother the velocity gets. And when you're closer to the sun, everything is much more turbulent. Velocity is much more varying and so on. Very clearly seen here. So basically, velocity fluctuations smooth out as you go away from the sun, yes? And close to the sun, everything is very turbulent and dynamic. So it means when we go even closer than Helios, it should be really crazy, yes? And this is basically what happens. So by Parker Solar Probe, these are data from Parker Solar Probe, zoomed in data. If you go really close to the sun, things are getting more and more dynamic and turbulent. And one thing that one has discovered, or one is studying a lot with the Parker Solar Probe, is that this here, if you look on velocity, and there is a magnetic field. So the red one, magnetic field, it has very large fluctuations, and sometimes it even flips the sign. So the red is like a zero line for magnetic field, and then there are these flipping of the sign. So what they call for switchbacks, yes? So very energetic. And you can notice that magnetic field velocities, they go in phase, yes? And going in phase, this is exactly what you expect from LVN wave to do. In LVN wave, magnetic field and particles move together. Velocity fluctuations, magnetic field fluctuations are in phase, or exactly antiphase. So it means all these structures that you observe here, these are LVN waves coming out from the sun. They get pretty nonlinear, yes, so you can see very steep. It's not like some nice sinusoidal waves, but everything which is coming out is like galvanic turbulence with a very large amplitude. So studying the properties of these switchbacks and these galvanic waves as you go closer and closer is really important with these missions to do. This is more details of the switchback, yes, so this is how a picture can look like. So the switchbacks is kind of folding in a magnetic field flux tubes which are coming out from the sun when they're blowing away from the sun. Okay, so that was a bit about the solar wind. So there is a lot of results coming out and will come out in the nearest years. And we are also in a very good situation because now we have a solar maximum, yes? So basically when one launched the missions, we were in solar minimum, nothing happened. So everybody was like a bit even worried. But now we are really in a solar maximum. There is a lot of CMEs, a lot of activity. So there is really a lot of data for scientists to study. And this solar cycle was even more active than was predicted. Yes, so one predicted some kind of smooth, maybe not so active cycle as the previous one, but it's really hitting quite hard now. Really nice cycle, a lot of auroras everywhere. So now I want to spend a few words about Earth's magnetosphere. So what is happening with this solar wind which is blowing away? And one thing I wanted to say is that basically the region where we have spacecraft in solar system, it's expanding. So I was showing you Parker Solar Probe. We are getting closer and closer to the sun. At the same time, we have Voyager 1-2, launched 1977, which are leaving the solar system, yes, and they're still operating. It's really admirable that it's 50 years, yes, and they're going strong. And it means that in this region, in between these two spacecraft, basically we have two types of missions. We either go to some places where we have not been, and Parker Solar Probe, example, like exploratory missions, or we are returning to the same place, but it means we need to come with much better equipment. So we really do more detailed studies of the site. And if you take Earth's magnetosphere, we have had a lot of missions before. So what you're doing, it means that the places where you go again with a spacecraft, it's kind of becoming a space laboratory. You go with a better equipment and you do much deeper studies. And that means that Earth's magnetosphere, which is here, so solar wind is blowing. You have seen such pictures before, I think. So here is magnetic field. So Earth's magnetosphere becomes a really great laboratory for plasma processes. So you can do studies by spacecraft, which you cannot do in a plasma in a laboratory. Everything which has to do with the plasma, with, for example, kinetic physics, distribution functions on kinetic scales, everything, you cannot do it in laboratory. You need really to go in space and you can do measurements like that. And Earth's magnetosphere is really great for that. So if we go to Earth's magnetosphere, a few words about Earth's magnetosphere. So if this is the Earth, this is the moon. If you would take a picture, you would see the stars, nothing is there. You cannot see the plasma, which is there, yes, not like remotely. Of course, by spacecraft, we know how it looks like. We know there is a magnetosphere. We know that there is magnetic fields, stretched tail. We know there is a plasma sheet, yes. And we know that, let me show, solar wind is blowing. By the time it has come to the Earth, it has decreased temperature, 50,000 degrees, but due to the plasma processes that we have here, mainly due to the reconnection on the day side, on the night side, we have this plasma sheet, which is up to 100 million degrees hot. So here, plasma is 100 million degree hot. And due to all the plasma velocities, all the active processes which is there, you drive also field-aligned currents. And in the regions where you have this plasma sheet, that maps to the regions where on the ground we see aurora. So basically, the places where we see nice aurora, they map out to these regions of plasma sheet where we have 100 million degrees plasma out in the space somewhere. It's kind of a nice connection from aurora to places where we know what is out in the space. It's the plasma sheet, really hot plasma sheet. So one has been studying a lot this region. So there is a lot of topics, you know, how we get these 100 million degrees day side, night side, shock studying. So there is a lot of mission. In the last years, a lot of data have come from Cornerstone 2 missions, like 4 spacecraft missions. One is ESA mission cluster for spacecraft. Now they're starting to burn up in the ionosphere. One is already burned up in the next years. The rest 3 will burn up. And another is MMS, NASA launched 2015. They're covering plasma at different scales. It's nice when you have 4 spacecraft. It's a bit like triangulation. So if you have 4 spacecraft, by measuring how things hit 1, 2nd, 3rd, 4th spacecraft, you can tell how things are moving in space, all the boundaries. So for example, if I go here, if I'm crossing some boundary, for example, if this tail is moving up and down, if I have 4 spacecraft, I can tell exactly how it is moving, with which speed and so on. But of course, life is not so simple as these simple boundaries. This is how these spacecraft look like. When you do numerical simulations, if you go and look in a real data, very seldom you see some nice boundaries out there. Everything usually is, especially where things are happening, where energy is being transformed, where important things are happening. Things are really turbulent and complicated shapes. And if it's complicated shapes, with 4 spacecraft, you cannot anymore do these methods because it has limitations. There's always this assumption about like nice boundary. So what is happening is that one is moving, to understand these complex processes, one is moving more to constellation mission, which means one needs to have more than 4 spacecraft. So for example, here is a NASA mission, which was selected 2022. MIDEX mission, this is heliosform to study solar wind. So we have a mother spacecraft, and then there is 8 daughters. So together 9 spacecraft. Going in an orbit around the Earth, but it is all the time spending a lot of time out in the solar wind. And by that, you can start to study the complexities that you have in the turbulence in all these processes that is in the plasma. So one is moving in that direction. The same is occurring also on ESA side. So currently, For example, there is a plasma observatory. It's in a pipeline, so there is a M7 call for ESA. There is a phase A studies. There are 3 missions in competition. This is one of those missions which is in competition. Yes. So again, we have a mother plus 6 daughters. So we need to go beyond these 4 spacecraft. And if things are successful, then basically we are, if this mission is launched 2029, I think, or 26 here, yes. Then here we are talking about launch at the end of 2030s, yes. So it's very long timescales we are talking about when we think about missions, preparing the mission. But that's where one is moving. So all the physics is complicated. Here is example of the shock, heating at the shock. You know, you can see how complex this environment is. One needs to have this separation of satellites at different scales to really understand the complexity of these energy conversion processes. Okay, and then I wanted to show one thing, yes, because we are talking about Earth's magnetosphere, about this current driving aurora. I wanted to show example how one can use Ventspils radio telescopes. One can use them for many different things, and I think Mitris will show about the sun, how you can watch the sun with them. But you can also watch aurora with them, for example, on Jupiter. Because the places where you drive aurora, that's very strong radio emission sources. But this radio emission cannot propagate to regions of stronger magnetic field. It means here on Earth, we cannot see radio emissions from our aurora, because where it's generated, magnetic field is weaker and it cannot propagate down to there. But we can see radio emissions from the Jupiter, because it's generated at a stronger magnetic field than here we have at ground. And this is an example where you connect Irbene. Here is Irbene. You can connect together with other stations, including the US. So you get a very large baseline, and you can start to observe Jupiter aurora in radio waves. This is decometric radiation. So by seeing at different stations, you can really tell from which place this decometric radiation is coming. So you can use Irbene not only to look on the stars, not only to look on the sun, but also to look for space physics processes. And finally, do I have a few minutes? How many? Here? I wanted another topic to bring up about talking about this heating. So now I talked about hundreds of million degrees, yeah, 100 million degrees, both at the sun was million degrees. Now I want to go to a cooler place, and this is ionosphere, like going from solar wind, magnetosphere, and down to the ionosphere and atmosphere. So if you look at the altitude, this is altitude in kilometers, and this is basically the ionosphere where you have the density of electrons, the red line, yes. So the highest peak is like around 300 kilometers, and then lower you still have a lot of electrons. And if you look on the aurora, the light of aurora is coming from like 100-kilometer altitude here. So here, zero glow aurora. And this region here is very important region for coupling of magnetosphere to the atmosphere, yes? Because when you have currents coming from the magnetosphere, they are going through the ionosphere, yes? And due to the resistance here, they're heating the plasma, and plasma can heat the atmosphere there. So let's look at the picture here. And here, what you see is ionosphere. So this is again altitude. So ionospheric density. And this is the temperature of the atmosphere, of the neutrals. So when we are at the ground, of course, we have room temperatures, and we go up. There's troposphere, stratosphere, mesosphere. So temperature is going up and down, but around room temperature, yes? So, but then when we pass like 85 kilometers, you see the temperature rises to well above 1,000 degrees. So that's when we enter the thermosphere. If you go higher up, it's even exosphere. Exosphere where no collisions yet, but in thermosphere you still have collisions, but temperature is like 1,000 degrees. And this increase of the temperature, yes, it corresponds to this region where ionosphere starts. So basically, that's the region also where you have currents going in. So currents coming from magnetosphere, they close here at these altitudes. Particles which precipitate from magnetosphere, they lose their energy here, yes, dissipate their energy. So the reason of this temperature increase is very much dependent on what is happening in the space, in the magnetosphere. Yes, and that's why, that's how space processes can affect the neutral density of the atmosphere, neutral temperature, and later also density of the atmosphere. I will show you in the next plot. But here, before that, I wanted also to show this so you can compare. Here is a satellite altitude. So imagine we run a satellite in a circular orbit around the Earth. And this is what is the lifetime. So how long time it will be in orbit before it's burning up in the atmosphere. So when you are at 200 kilometers or below, basically satellite is burning up directly, yes? And when you go above 200 kilometers, yes, it takes a few days. If you're at 300 kilometers, it takes 1 month before it burns up, yes? And you see there is 2 lines here. One is solar maximum, solar minimum. So at solar maximum, it's burning up 2 times faster, yes? So how, if we go back to this picture now about the temperatures that I was telling. So now, if we have solar activity or not, it means there will be more or less current flowing in the ionosphere. It will be more or less particles precipitating from ionosphere into the ionosphere. So the temperature of the neutrals will rise, the atmosphere temperature will rise. And when temperature is rising, you can compare here. So here is the temperature. When it's not much activity, maybe it's around 800 degrees. When it's really a lot of activity, then it can be 1,400 degrees. If atmosphere gets hot, it expands. So the density at high altitudes should increase. And that you can see here, total neutral density, yes? So if you are, for example, at 300 kilometer or 500 kilometer altitude, yes, then between the active and non-active solar time, the change in density can be several times. So density basically several times can increase. Yes. So when we have active time, then density goes up. Why it's important? Why I wanted to show this. This is, let's take one example, Starlink. So now it's more than 7,000 Starlink in orbit. I wanted to take example of 3rd February 2022. So before 3rd of February 2022, to launch a Starlink, one has the following procedure. You launch a rocket to 2,010 kilometer altitude. You disperse your spacecraft there. Spacecraft do some initial tests. And then you use electric engine to reach the 550. So they need to, okay, plus minus, but they need this 550 kilometer altitude to go up. And why you want to do like that? Because electric engines are very efficient, yes? So you want to use as much as possible electric engine. So you leave it at 200 and then it slowly goes up to 550 kilometers. So you can bring many spacecraft up. Okay, so what happened 3rd of February 2022? Yeah, there was a geomagnetic storm for several days. Very strong geometric storm. There was CMEs going on. So it means atmosphere is getting heated, density goes up. Okay. So what happened? 49 Starlink spacecraft were launched, and during the next days, 40 spacecraft burned up in atmosphere. Because the friction increased so much that you could not do your initial test, you cannot bring them anymore with electric engines to the higher altitude. So really important to follow the space weather conditions. So what is the procedure now? One has changed the procedure after 3rd of February. You launch to 300 kilometer altitude, yes. Then you do your initial tests, and then you do climb up by electric engines to 550 kilometers. Now, it seems like, what does it matter, 200 or 300? So when you go to 300 kilometer altitude, you cannot anymore bring 49 satellites. You can bring, I think, less than 40 satellites up. Yes, higher you want to bring, less spacecraft you can bring up. So of course, economically, you suffer, but you need to follow the safety so that the space weather conditions do not affect you. And this is just a line showing how International Space Station, it's at 400 something kilometer altitude. So one can see that, for example, that station regularly, yes, like every month or few months, you need to do this altitude racing maneuvers, because all the time your altitude is decreasing due to the space weather conditions. And of course, this decrease can change sometimes slower, sometimes faster, depending on what are the space weather conditions. Now, this is really important region for all this. So heating atmosphere, ionosphere, what is happening, but what is interesting is here satellites cannot circle in this region because friction is too high. Balloons are flowing below this region. So there is really no good access to get in situ data from there. So we have some remote observations, we can observe aurora or something, but there is really no good data to study this region. Yes? So this is like closest space region that we have, but it is really the least accessible or the least least data we have from that region. There is one way how you can study this region. This is sounding rockets, yes? So sounding rocket, it means that you launch a rocket, it flies up, and then it falls down. But one needs more data, you know? So then there are different ideas. So one idea, and these are still like mission concepts, they are not going to be built, but hopefully in some distant future, 10, 20, who knows, 30 years, there should be. This is one last such concept that was for a few years ago done. Mission Daedalus for ESA, it was studied, yes. So basically, if you build your spacecraft as a long pipe so that friction is as small as possible, yes. So your cross-sectional area is small and spacecraft is large, yes. Then hopefully you can, in this picture that you have, your spacecraft can do some kind of dives, yes. If orbit is elliptical, then it can do some dives in this region, and in that way get a lot of data, you know, from that region. Those type of concepts are studied, and it's time, or no? Ah,
No.
I thought it's
Sorry.
no problem.
It's also time.
It's also time, yes. So that's something to come in future. As long as we are not there yet, still the best way to do this thing is through sounding rockets. So as I was telling you, have a rocket, it's launched, it goes up and it falls down. And during this launch, you can do different things. And also there, one development which is ongoing is that you are having a rocket, yes, like this, for example, you launch. But again, if it's just a single point, you have always a problem of telling from where things are moving, how things are going. So you need these multi-point measurements. And what you do, you take a rocket, it flies up, and then it throws out several units. So in this case, for example, from this rocket, 8 such units were flown out in different directions. And from that way, from multi-point measurements, you try to tell what is happening up in a space, yes. So here is these eight units. The launch is up in northern Sweden. This is a rocket, yes, and you launch. It's just a few minutes of data, and that's it. And maybe you have several years to build this rocket, yes. So basically, the data is very sparse and very few from these regions that I was showing to you. By the way, here soon will be also normal rockets launched from this area, from S-range, hopefully already this year. Yes, so this was the launch 2020, yes, of this rocket. You see Aurora in the background. You wait. This is really nice thing about this sounding rockets. So you really have a button, yes, you wait space weather conditions, you wait the right conditions, right Aurora, okay, push a button, and then you get the data. But you see, you need to work like year or more to build this rocket, and then it's just a few minutes of data, and that's it. So we really have this region where we have very few in situ data. Yeah, these rockets are really nice for student teaching, so one can do like, even students can build these modules and to study whatever in this region. So this is really, from educational point of view, really nice sounding rocket experiment. Yes, and the last slide, so that was it. And then the last slide, just when it comes to this studying the space and everything, launch. So very important is to launch. So things are getting complicated. So for example, if we take ESA, also a bit NASA, so there becomes larger and larger distance in the launch between the missions. This is one of the problems that we observe. So it means if you have to wait 20 years, engineers lose experience and everything. So things are really getting slow, let's put like that, both at ESA and NASA side. But it's important to launch. Whatever way it goes, you have to launch as often as possible. So here, for example, was clusters that I was telling. First launch was not successful. It was Ariane's first launch. There was engineering errors, but it was relaunched 2000, and at the end, it was really successful mission, you know. And here is a launch 2018. It's on the way to Mercury, so we will reach next year. There will be a lot of data, you know. I think it will be really great mission. Here was a launch, I don't know if one can see, of the sounding rocket, how it can look like, yes. Oh, this Zoom connection is too bad, but here was a sounding rocket going up, yes. So, and also I wish success for launching the space air chair, yes. Launch. That's it. So just a short summary. So I was telling about source of solar wind, yes, Parker Solar Probe, closest to the sun, solar orbiter. So really golden age for solar wind studies. Earth's magnetosphere, this transition from 4 spacecraft to multi-scale spacecraft missions, which is occurring very important in the next years. And this region of magnetosphere, ionosphere, atmosphere interactions. This is closest, least explored region of space. Really important also to study from such a point. Thank you. Yeah.